So I'll record locally to my computer and then upload manually instead of via the Zoom tab. It'll show up on one of the pages of content videos. Suppose we were interested in asking some additional questions about the relationship that you observed in the stopping distance activity on Pivot Interactives. It was actually in Canvas, it was called Kinetic Energy and Work, I think, with a question mark there. Kinetic energy as defined this way, and particularly in relation to the graphs that you made between the distance required to stop the puck as a function of its initial speed on the cart on its way in. And your data, I think, showed that this relationship is not linear, but that if you graph instead versus the square speed, that it becomes linear. So if we make this definition, it seems to me that speed squared has something to do, some sort of relationship to a friction force applied for a distance. Might also have something to do with a friction force applied for some amount of time, the time that it takes to come to a stop. But we do have a relationship between the square speed, which is to say, just is directly proportional to the kinetic energy. So we apparently have a relationship between kinetic energy and the distance over which friction acted. We might be interested in aggregating, in like accruing the effect of a force that acts for some displacement on the motion. How does a force acting over a longer displacement affect the motion differently? The force applied for a distance, I keep saying that, greater the force, if the force is bigger for the same distance, okay, it's more. If the force is the same but the distance is longer, it's more. Force applied over distance. We're just talking about a product. We could define work, capital W, as the product of force and distance. Because I'm thinking about this stopping distance activity. Friction force applied for a distance has some sort of effect on the speed. It reduces it to 0 in this case. Force applied over distance. What is that? How does that thing behave? What is it? Well, all right, I'm going to call it work. I have a couple problems with this definition. Force is a vector. And frankly, so is displacement. Now, if this new animal work is going to have something to do, going to say something about the relationship we observed in the activity, a force applied for a distance should be relatable to the square speed. Now, square speed, that's scalar. When kinetic energy asks for v squared, one way to write that as velocity dot itself. So within this definition, there's a dot product, which is good because we need some kind of product here to multiply these two vectors. Why did we need to define the dot product in the first place? For this. The other trouble I have with this what if the force is changing for some reason? Maybe the force is changing direction or changing magnitude or both. Maybe the angular orientation between the force and the displacement is changing. I don't know. And if it's changing, then we might have to account for the fact that it changes. Strictly speaking, this definition, which is perfectly intuitive, I will argue, based on the stopping distance activity that we looked at last week, is actually a special case of a more general thing. There's no problem here. This equal sign is real. If the force isn't changing, then the sum of all the very, very, very small displacements is just the overall interval displacement. But what if the force changes? As we move in a particular path from position 1 to position 2, we do so subject to some force, which may or may not be a function of where we are. Thinking about a trampoline. If I'm standing on a trampoline, kind of at rest, and I jump a little bit, if I depress the trampoline a little bit, it'll push back on me and I might, hop. But if I jump a lot, it'll depress a lot and push back a lot. So the force that I'm feeling is a function of how far I have moved from my equilibrium position. The force is a function of position. If we would like to aggregate, sum the total effect of such a force that acts on us through a displacement as the magnitude of that force changes, we need this equipment. This is a path integral, technically a Calc 3 kind of thing. This looks like multivariable calculus. We won't actually treat it that way, but yeah, technically this is a Calc 3 idea, a path integral. Our strategy for attacking such a thing is always to unpack the dot product first and rewrite it using what we know about the dot product, either in terms of components or in terms of magnitudes and the angle between, to rewrite in terms of a single scalar variable so that we can integrate like normal, essentially. Because it looks kind of weird. There's a dot product in my integral, in my integrand. That's weird. I know, but let's just work from the inside out. Let's address the dot product, and then we end up with a normal integral like we're used to. Force aggregated over distance. Maybe it is the case that the force is not a function of where we are. And then we can pull it outside the integral and we end up back here. But if it is, we need to make sure that we start from this configuration so that we're prepared to handle that. All right, so what are the consequences of this definition here that we've got? Suppose the force that we ask about is not just any force, but is the net force. So that we could argue the whole story, all the forces added up, act for some displacement. What is the work associated with all of them? What is the net? Yeah, what is the net work associated with all of the acting forces? Mm-hmm. But according to Newton's second law, and that's why I've labeled this equal sign N2, this first one is a definition. There are three equals here. Three lines is defined to be. That next equal sign is Newton's second law brought to bear. The acceleration is the time derivative of the velocity. And if we're being careful, the dot product. We take the x component of one and multiply by the x component of the other. And then we add that to the y component of one times the y component of the other, and so on. So we end up with that. But dx divided by dt, that's the instantaneous horizontal velocity, or I guess not horizontal, but the instantaneous x component of the velocity. And dy divided by dt, that's the instantaneous y component. And this integrand is not tagged anymore for the original variable. We have done a differential squishing. We've combined the dr with dt and ended up talking not about dr but dv. So we've got this integral tagged for v now. So this is going from velocity 1 to velocity 2. It's a little bit odd that this is a vector velocity and the integrand is scalar anymore, because we just took the dot product. We know it's scalar. We should really have scalar bounds. For now, I'm just going to say state 1 and state 2. Integral thing d thing is thing squared over 2. And we don't need to worry about integration constants because we're going to evaluate from state 1 to state 2. We factor out m and the division by 2. We've got vx squared plus vy squared plus vz squared, which looks a lot like the magnitude calculation for some vector v. It's what we would get if we did that. From state 1 to state 2. So now I can happily, let's assume that the mass of this thing hasn't changed so that we need to figure out what it is in state 2 versus what it was in state 1. Our velocity in state 2, and then we subtract what we get which, call me crazy if that doesn't look like the change in some quantity kinetic energy. My favorite thing about this is that it is entirely rigorous. We have made no assumptions except for the constancy of the mass. That's it. If we haven't somehow lost or gained matter along the way, this is entirely rigorous. No assumptions about the constancy of the force, no assumptions about the relative orientations of anything, no assumptions about needing to not worry about the vector nature. We have accounted for all the pieces, and we have proven, according to our definitions, that the net work must be equal to the change in the kinetic energy of a thing. This is the work energy theorem. It's what is called the work energy theorem. Technically, it's just Newton's second law again, with a couple extra definitions. We define work, we define kinetic energy. Oh, look, Newton's second law has told us that work and kinetic energy are related. Just like we expect them to be. A force applied over a distance should be proportional to the square speed. The slope of this relationship, I expect, has something to do with the friction coefficient and the mass. Ooh, or maybe just the friction coefficient. Friction depends on the normal force dependent on the mass. Maybe just the friction coefficient. That's pretty cool. Maybe also like G, like maybe there's a 9.8 rattling around in there. How do we use this thing, this path integral? I'll give you an example. Suppose we are sitting on a tire swing. And suppose someone pushes us to try to get us through the stylus, to try to get us moving, but pushes us in a very particular way. Very slowly. pushing horizontally only. With a magnitude, only the magnitude that is required to keep us essentially at rest. You could think of this as an idealized process. We do this so slowly. If you looked at it at any moment, it's like it's not moving. It's like watching fingernails grow. Always with net force 0, but still in motion eventually. Eventually, it's a really boring swing ride. Eventually, we get to the situation where the string holding us up makes an angle theta with the vertical. In order to do that, we followed a path, like a path integral. We followed a path. That path, complicatedly, is a circular arc. The string, or the rope, I guess, holding up this tire swing has a particular length. I have 3 questions. How much work does tension do? How much work does the applied force do, moving us from one position to the other? Actually, I have 4 questions. What's the net work that is done? I think you know the answer to that already. And how much work is done by gravity? All right. Let's answer these in order of straightforwardness. What is the net work done if we do this entire motion in equilibrium without changing our speed? What is the change in our kinetic energy? Our speed is 0 at all times, essentially, we're arguing. And if the change in kinetic energy is 0, the net work done must also be 0. Let's talk about tension. The work done by the force of tension is calculated according to our definition. The force of tension dot dr integrated. I'll just write over the path. There are limits, I don't know, whatever. I guess from theta equals 0 to theta equals something. We'll make that a fixed constant, theta sub 0. But here's the thing. The tension in the rope is directed radially up towards the point where the rope is mounted. Our displacement at all instants is tangent to the path. The path is a circle. The tangent of a circle is always perpendicular to the radius. I don't know the magnitude of tension. I don't know how it depends on angle, and I don't care. At least not for this question. The force of tension might have some theta dependence. As we change the angular orientation, maybe it changes. I don't know. The magnitude of the force of tension might change. The size of the steps of the circular arc that we're making, I guess we can keep those constant. But the important part, the dot product asks for the angle between. And the angle between is always, because a radius and a tangent to a circle are perpendicular. Zero. This is the great thing about the dot product. If perpendicular, we know zero. All right. What about the applied force? Well, the applied force is not always perpendicular to the displacement because it is horizontal all the time, and our displacement changes direction. So we're going to have to be a little bit more careful. What applied force preserves the equilibrium at any given moment? We need a free body diagram. Let's draw it for some arbitrary angle theta. What forces act? Well, we've got gravity, the tension in the string or the rope or whatever, and the applied force. Okay. I don't see any reason not to use traditional axes. Up, down, left, right, at least, won't change as we go. If we tried to rotate, then we'd have to keep rotating the system as we went. I don't want to do that. Since we are told that we are to stay in equilibrium the whole time, both accelerations need to be zero. We we can't accelerate in any direction. Okay. Horizontally, our applied force and, oh, wait a minute. We've got the left going component of tension and the upgoing. The angle theta, let's see, alternate interior is this angle. So the horizontal component is opposite, and that's sine. Oh, shit, wait a minute. Applied force. That's just horizontal. Tension goes the other way, according to the magnitude and the sine of the angle in question. Vertically, the up component of tension and the weight down. What is it we're trying to find? We need the work done by the applied force. So we need to know what the applied force magnitude is. All right, so it's applied force we want. So we need to solve this one. And plug that in here. Mg over cosine times sine equals 0. The applied force then is equal to mg tangent theta. That's the strength, the magnitude of the horizontal force that we need to stay in arguable equilibrium the whole way. As theta increases, so does this force, and we just adjust with it. Okay. The work done by the applied force, the integral over the path of the applied force dot the displacement. We know the magnitude of the applied force. It's that, we just found it. Mg tangent theta. In the x direction, I guess, because it's always horizontal. There's a couple different ways to think about the next step. One way involves asking what are the components of the infinitesimal displacement vector dr. Clearly not infinitesimal here, but I needed to draw it, right? Its x and y components are specified according to its magnitude dr, and its orientation. Now, the displacement, we said, is tangent to the circle, perpendicular to the radius. Let me zoom in a minute here. The radius and the displacement are perpendicular because that's how circles work. But the x and the y axes are perpendicular. If this angle is theta, then this angle is 90 minus theta, because brown and green are perpendicular. But if that angle is 90 minus theta, that angle is theta again, because x and y are perpendicular. So if we think about the components of the displacement, dr is the displacement, and the components are sine and cosine. Cool. One way to think about this is the way that we're doing now. I'm starting to feel like theta is my scalar variable of choice. It has to do with the bounds of the motion we're considering. We start with theta equals 0 and we go to some angular orientation. And I start seeing it pop up. So I'd like to talk about only theta. Right now, the differential dr is still what's tagging the integrand. That's an infinitesimal displacement along a circular path. It's an arc length. It's a very small arc length. For a circle of radius r, where theta is expressed in radians, the arc length s is given by this formula. We know that because the circumference, the total arc, is 2 pi r. 2 pi radians is once around a circle. So if we took a derivative of a circular arc, now the circle has the same radius regardless, we just need to take a small amount of angular motion is associated with a small arc length r d theta. And now we can convert the integral as written into an integral in terms of theta, a single scalar variable. I'll do both things in one step. The dot product, we only the I dot I survives. I dot j, that's 0. Where now we can label the integration bounds because we know exactly which variable we're talking about. Integral of sine is negative cosine. Negative cosine of theta 0 minus what we get when we plug in the other bound. Minus the minus gets us a plus. The units for work are the same as the units for kinetic energy, by the way. Kilograms, meters per second squared, meters. Cosine is dimensionless. This thing in parentheses doesn't have a dimension. So we've got kilograms, meters squared per second squared, which is a mouthful. So let's define this as joules, Joule. I said there was another way to think about this dot product piece. the magnitude of the force. Remember, there are two versions of the dot product, one by components and one by magnitudes and angles. The magnitude of the force, the magnitude of the displacement, and the cosine of the angle between them. The force is horizontal, the displacement is at an angle theta. We wrote that already. Magnitude, cosine of the angle between. We still have our variable mismatch, but again, let's rewrite in terms of circular arc displacement. And we're back. We're going to end up doing the same arithmetic either way. It's just a matter like whether we think about it components or whether we think about it in terms of magnitude, cosine of the angle. It's the same story. There's one more part. Part D, the work done by gravity. Let's find it two ways. There are three forces that could possibly do work. But we have already said that the sum total of all of it has to be zero. We've said that the tension doesn't do any work. It cannot function to change our kinetic energy. It only serves to redirect us. The work done by the applied force we just found. So the work done by gravity must be the negative of that. The dot product, remember, evaluates negative if the angle between the two vectors is obtuse. If the two vectors are anti-parallel more than they are parallel, then the dot product will be negative. And when we integrate a negative over some path, we're going to end up with a negative result, like we do. Okay, so that's an argument from what we think the network needs to actually be equal to. What if we did it for real? The force of gravity is constant. It's in the negative j direction. the mass, gravity, it's all constant. Could bring out the minus sign too. Why not? Whatever the circular displacement is, dot J, that's delta Y. It's the overall vertical displacement. Where integrate dr, that's overall three-dimensional vector displacement. Dot with J, only the Y component of the displacement survives. That's this. That's delta Y. What is delta Y? From where we started, we've moved that far. Whatever the difference is between the length of the thing. Oh, I'm sorry, I apologize. I've been using capital R, but I had originally defined it as lowercase l, so I'll just fix that here. Apologies. That total distance R, whatever the difference is of this shorter length. Now, the hypotenuse of this highlighted triangle is still R, and we know theta, so this length that we are, like, we've moved up a certain distance because vertically we still have this far to the top. How far? Well, it's, let's see, hypotenuse cosine theta. So how far did we move? The difference. Yep. Correct. Either way, we slice it. Questions, comments, concerns? Excellent. I know that's a lot. Hopefully, it felt like a lot at first, looking at the dot product inside the integrand, and then what the hell is a path integral? Rewrite in terms of a single scalar variable, and then we can integrate like usual. Hopefully, this feels more straightforward now. I think some practice might be in order, but first, let's take a break. I've got about 4:25. Let's take 15 minutes. I'll see you back at 4:40.